Exam 3, I changed the exam date to November 9th instead of November 6th because it didn't seem like you guys would have enough time to actually do all 3 homework assignments. So I pushed the exam date to Monday, November 9th. Okay, hopefully that's okay with all of you to give you extra 5 days for the exam. Okay. The first on the wire worksheet is due 26th. That's Monday. Okay. And here's some other deadlines. The DC circuits is due, WebAssign 7. And make sure you read chapter 30 in the textbook. Now, the other thing is I sent you folks an email regarding exam 2. And exam 2 average is kind of low. And you know, as I looked through the exam, especially the first problem, I really didn't foresee the number of ways that the solution to problem 1 could go wrong. I thought that would be more of a straightforward problem, but I didn't foresee how many ways it can be done incorrectly. And I figure it's you know, like for that one, I really think it's a problem you should know how to solve. Because I've done a few of them. So I figured for problems like that, and some of the other problems too, you really need to go over those problems. And so I figured, okay, let me give you another chance on those problems and have you rework them. So from problems 1 through 4 on the exam, rework them. And I'll give you 50% of the points you lost. That way you get to see maybe where you went wrong. And I give you some hints in the email I sent you. For example, problem 1, just treat those 2 capacitors as one single capacitor all the way through to the end until you answer the question, what is the charge on each capacitor? Okay, just treat it as you have just the 2 capacitors in series, replace it with 1. And then do the charge sharing problem we had done in the homework. Okay? Remember, charge, once you connect a 2 microfarad capacitor, charge will move in the wires until the potential difference across each of the capacitors is the same. And what I mean by each of the capacitor, the 2 microfarad capacitor and the single capacitor that represents the 24 and the 8 microfarad capacitor. Okay. Problem 2, most people did okay. Some people made it extremely difficult because you should have been able to set up problem 2 using Kirchhoff's laws, but each one of the equations should have just had one unknown in it. Some of you guys also had engineering. Yeah, that happens. I'm sorry. I mean, the fact that you have a couple exams on one day, it happens in the sciences and engineering. But anyway, I want to make sure that these, you guys go over these problems. I didn't do that in the first exam just because I know that first unit is hard, and also the average wasn't as low as this one. The average on this test was below 50%. Okay, which I never envisioned. I envisioned maybe the exams would be lower, the exam average would be in the 50s, and that's why I need to curve the exams. But I didn't envision it to be this low. But I also didn't envision number 1 to be as difficult as I thought it would have been. So anyway, you get the opportunity, and it's a lot of points you can make up. I think if everybody takes advantage of it, I think everybody would, if they get all the points, they will probably be at the point where they would have passed the test, which in my class means above a 60%. I think almost everybody would be above 60% if they take advantage of this. Problem 3 You did not need to solve for time at all. And that's one of the points I was making in the capacitor problems. If you really don't need to use the time equation, don't. In fact, in that particular problem, I actually went through and solved for t in that problem just for fun. It took me a while because in that problem, this was 2.2K, 5.6K. Okay, in that problem, if you're going to solve for t, you have to set up two equations. You have to set two equations to unknowns. You got to use Kirchhoff's laws. One, realizing that if this is I1 plus I2, that's I1, that's I2. Okay, I have to now use two loops because I have two independent currents. Maybe choose this loop and that loop. So you have two equations with two unknowns, and they're differential equations, and you got to solve for Q2 and Q1, which takes a little bit of work. On an exam, at least in this course, it would take a while. Okay, you might get a problem like that in maybe a Math 33 exam. But in the Math 33 exam, you just have to do the manipulation, not derive the equations. So it takes a while. But you can do the problem without solving for time because you can figure out the maximum current. Because this acts like a wire, t equals 0. So all the current goes through here. Once you know the maximum current, you multiply by 2/3. And so this guy is going to get 2/3 of the maximum current. Well, resistance times current gives you voltage. And then you can figure out the voltage across this guy. Okay? So I want you to go through that problem and try to solve it. Do not use any time in the equation. Okay? Unless you're a glutton for punishment. No, it's not asking for time. It's asking for the charge in the capacitor, and it's asking for the current in this branch. Okay? He's only asking for the charge in the capacitor and the current through this branch when I is 2/3 of its maximum value. I from the battery is 2/3 of its maximum value. So if you don't need any value for t. Okay. Although I did go through and calculate it. It was like, I forget it already. It's like 0.63 seconds or something. Okay. But don't do that. Okay. Because you have to have the right equation for I. Just use the fact that you know what the value of 2/3 of the current is. You know how to calculate voltage across this from Ohm's law. I mean, really, it's an Ohm's law problem. Okay. You're not using the Q equals Q max times 1 minus e to the minus t over RC. You're not using that at all. You don't need to use it at all. Okay, and in fact, that equation is not really correct because that equation is just for our RC circuit with a resistor and capacitor in series. Okay, the fourth one actually was not if you see it, it's not a hard problem because in the fourth one, you have, and I'm trying not to erase this board. And I don't want to give too many hints because I kind of want you to think about them. You have a square. Let me draw the coordinate system. I define my coordinate system to be here. You can define your coordinate system however you wish, but this is how I did it in the problem. Particle lands here, and you want to know how you can calculate where that landed based on you measuring this current, that current, that current, and that current. Okay? Well, somewhere on here, this is a resistive device, so the electric potential will vary across there. But the thing you know is that V here and V here are the same because the surface of a conductor is an equal potential. And so the potential difference from here to here, let me use a different color. The potential difference between these 2 points has to be equal to the potential difference between these 2 points. They have to be the same because we know that this point and this point is at the same potential. It's a conductor. And this is some potential, some intermediate value. And you know Ohm's law. Ohm's law will tell you that if this is, let's say this is I sub B, and this is I sub B, now, what's R? Well, R is the resistance from here to here because the current's traveling along this length. And you use the equation R equals rho L over A. Well, where L is this distance for this resistor, and for this resistor, L is this distance. Okay, and you can do the same thing in this direction. Oh, what's A? A lot of people have a hard time with A. The current's going this way, right? So imagine you have current going in a wire. A lot of people have a hard time visualizing this, and I used to too as a student. Let's say you have current going through a wire. Okay, maybe I should draw a picture. Current's going perpendicularly through this cross-sectional area of the wire. What's A for this one? The current's going, let's say the current's going that way. Okay. What's A for this particular case? It's going to be the thickness of the coating, the resistive coating, times this area. You got to think 3D. Right? I mean, you go back to here in the wire, this current is passing perpendicularly through the cross-sectional area of the wire. So what cross-section am I going through here if the current's that way? The cross-section is defined by the thickness of the coating times this area. That's what A is. Okay, so hopefully I give you enough information for you to be able to solve the problem. And so you want to write your final answer in terms of what you've given. You don't need to use any Pythagorean theorem or anything because the current's going this way. Right? The measured current. So you're taking everything that goes along here. You don't have to worry about stuff going this way. Okay, you're measuring everything going this way and you're measuring everything going this way when you're measuring the x coordinate. And then when you're doing a y coordinate, you're measuring everything going up and everything going down. Let me see, I'm trying to understand this question. Does each ground connection cover the whole flat face? Well, each ground connection each of these grounds really goes to the same point. They have to go to the same point. Okay. But I'm not sure what you mean with respect to this. There's a meter here, and I didn't draw it. There's an ammeter here, an ammeter here, and they are tied to ground. Yeah, the connection goes from the edge to the meter, from the meter to the ground. And you're right, it covers the whole side. Which is hard to draw. It's actually hard for me to draw that, but Okay, are we okay with that? So a couple of people got it correct. And I think one person did it exactly the way I wanted it. Some other people tried to use some intuition. Some of it was okay, and some of it wasn't. Okay. Anyway, please take this opportunity to go through those 4 problems and give yourself a chance to add some points to your exam. And you know, the final exam, the final course grade is still going to be curved, but you know, at least this should help most of you guys. Okay. You know, it might raise it's not going to raise the average to like 70%, but at least it's going to raise the average to something more palatable. So yeah, you're welcome. Okay, I'm not sure I'll be doing this for all the other exams, but I mean, for this one, and there was no score over 80 on this test. Well, that's the other reason. Okay, and like I said, part of the issue is trying to write an exam that has non-conventional problems, but the problems are doable. Okay. All right. So enough of that. Hopefully you can get this done by Thursday. So by Friday at 11:59 p.m. So what I want to do today, and if I don't finish this today, I will finish it in lab. I'm going to finish a chapter today somehow, either here or in lab. Okay. So I want to get through this chapter and keep on going because we're a little bit behind already. And so I'll probably use next Wednesday's lab to catch up a little bit. Okay. So I want to continue talking about the force on the wire and the magnetic field. I want to look at the torque on the wire, the uniform field, and the DC motor. I have a DC motor with me, but you know what I really need for me to show you this motor better. I wish I had another camera, but I'll try the best I can to show you this motor. Okay. Because you need to look at it up close. And then I'll do a brief discussion of the Hall effect, which is actually an important idea, but you usually don't discuss it much in the introductory class. So we left off the other day discussing the force on a wire in a uniform magnetic field. Just a second here. Okay. So we're looking at force on a wire in a uniform magnetic field, and the expression that we came up with was that the force is equal to the current times L cross B. And that really came from considering the force on a bunch of different charged particles contained in a volume within the wire. So what I derived assumed that B was uniform and the wire was straight. And in fact, you can also calculate the force per unit volume, because the equation that you see there, the A times L, is just the volume. So if you can think of it as your A times L as being very small, then your force per unit volume is Q V cross B times the number of charge carriers per unit volume. And if the magnetic field varies over the volume, then you would have to integrate over the entire volume of the wire to get the actual force. And I demonstrated this to you with the jumping wire demo. Okay. What if L is not constant? That's one question to ask. But before I go on, you have another cross product there, which means that you have to have another right-hand rule. Okay. In order for us to calculate F without evaluating the determinant, we can use the right-hand rule. So give me a second to erase my board, and I'll switch to the board. So if I wanted to use the right-hand rule for the force on a wire in a uniform field, let's say the current is this way. The magnetic field is into the board. Then I take my fingers, put them in the direction of the current, curl them towards B, the force is upward. I'll do it one more time. Put my fingers in the direction of the current, curl my fingers towards the magnetic field vector, and my thumb points upward. By the way, there's other ways to do this right-handed rule, but this is the way I was taught. Some people will do it with 3 different fingers and stuff, but I think this should be simple enough for us, okay? I cross B and F is upward. And you might be thinking, oh, what about conventional current versus electron current? Well, current depends on the product of Q and the drift velocity. Okay, so if electrons are moving this way, if positive particles are moving this way, negative particles are moving that way. So basically I'm changing the sign of both. That doesn't matter. Doesn't matter whether I use conventional current or electron current, I'm still going to get the same result because the sign of both of these changes. Okay. And then the other thing that I mentioned with the jumping wire was, did the magnetic field do work on that jumping wire demo? And the answer was no, because remember when I did the demo, I put the wire in the magnetic field, I turned on the power supply so that current ran through the circuit, and the wire jumped out of the magnet. And we said that magnetic fields don't do work on charged particles. And that seems like a contradiction. But the thing is, if you have a current carrying a wire, the electrons are going this way, and then you put some sort of magnetic field, let's say, into the board, the electrons are going to be forced to go in a circle. But the radius of the circle is going to be pretty big, bigger than the thickness of the wire. And so the electrons are going to collide with the surface. And all those electrons colliding with the surface, and they're moving fast, they're imparting momentum to the wire. And it's that force collectively of all the electrons hitting the surface of the wire that's causing the wire to jump out. That's what's doing the work. It's not the magnetic field. Now another question might come up. Suppose I have a car it's at a junkyard, and I want to pick up that car. What do I do at the junkyard to pick up that car? I put a big magnet, and it lifts up that car. Does that magnet do work on the car? You bet you. The magnet will pick up the car. It'll do work on the car, but then again, we said that magnetic forces do no work on charged particles. And I got to be careful, and I got to be more specific when I say that. If the magnetic field is due to a current, then it will not do any work on a charged particle. So B fields okay. This magnetic field is not due to a current. It's due to really dipoles. It's due to the intrinsic spin of within the atoms that make up that magnet. I'm trying to look at your question, Patrick. I mean, this is a big electromagnet just to lift the car off the ground. But magnetic fields that are produced by permanent magnets are due to the intrinsic spin of the atoms the intrinsic spin of the electrons in atoms. They can do work. Oh, okay. Sorry, Patrick. Okay. If the magnetic field is due to a current, they're not going to do work on a charged particle. If you take a dipole and put it in a non-uniform magnetic field, the magnetic field will do work on the dipole. Because the dipole is really not a single charge. So I got to be careful when I say magnetic fields don't do work, okay? But magnetic fields due to currents don't do work on charged particles. They do work on magnetic dipoles, okay? Magnetic fields can do work on magnetic dipoles. Fields that are due to the intrinsic spin can do work. Okay, so basically just focus, when I talk about what I said the other day, this is really due to currents. Okay? I just want to clarify that. And it's never discussed in a textbook. All right. Let me continue. So what if you have a wire and either the magnetic field changes or the direction of the current changes? Either when. Okay, let's look at the case here where the direction of the current changes. So I have a wire in a magnetic field. And the wire does that. It's carrying current I. We said that F is I L cross B. And this assumes B is constant, L is straight. And we want to look at the case where the wire is not straight. Well, all I got to do is break this wire up into a piece small enough so that this term is constant over that length. So I'm going to break it up into a small enough piece, we'll call ds, and we'll call the force on that piece dF. And then I take another ds and calculate the force on that piece. This ds is the same as this ds, and I go all the way along the wire, and then I sum all the df's. Well, that's not mathematically valid, right? I can't just say that. What I'm doing is integrating df. Of course, in this particular example, I is constant and B is constant. And so my F then is going to be I times the integral of ds. Oops. Cross B. And B is not part of the integral. What is the integral of ds? Let me answer your question in a second, Andrew. That's a good question. Yeah, ds is just the length of the wire. The ds, it just represents a displacement. So it's still L, but L is the displacement between these 2 points. L is just basically the displacement between these 2 points in the general direction of the current. So that's L. So I can still write it as L in terms of L, but L here is really the shortest distance between these 2 points. It doesn't matter how it's curved. It just, the distance between the 2 ends of the wire. Again, remember, I'm assuming the magnetic field is uniform. Please don't forget that. If the magnetic field is not uniform, then this becomes part of the integral. And I'll get to your question in a second, Andrew. I want to say one more thing. What if the wire forms a closed loop? What if the wire forms a closed loop? Then what? What's the integral of ds? In other words, you're integrating ds from A to A. You get 0. Correct. So the force on a wire, on a loop of wire, in a uniform magnetic field is 0. Remember, the field's uniform. If it's not uniform, that's not the case. Okay, let me answer Andrew's question. Does applying a magnetic field to a current carrying wire change the resistance of the wire, since it increases the amount of collisions that happen? That's a good question. I don't know if anybody's actually really measured that. Trying to think. You know, Andrew, I need to think about that. That's a really good question. I can't answer. I don't want to say something off the top of my head and be incorrect. Can I give you a response to that? I'll either email the class or I'll respond to you on Monday. Is that okay, Andrew? Okay. And if I forget, just bug me about it, okay? All right, that's a very good question. What if the field is not uniform? I'll give you a simple example. Suppose you have, and it's simple, but I have a hard time drawing this, okay? So let's say I have a bar magnet, and I have a loop of wire, in the magnetic field. Okay, I have a loop of wire in the bar magnet. So let's say I have, so here's a bar magnet, and I have a current carrying loop of wire in the magnetic field of the bar magnet. Okay. Let me find a good loop of wire. Okay, I have a lot of loops of wires as a coil, but let's say I have a bar magnet like this, and just focus on one of the coils that makes up this, one of the loops that makes up this coil. Then what is the force on that loop of wire? Well, it's not going to be 0 because a bar magnet does not produce a uniform magnetic field. You know, the bar magnet's magnetic field will look like this. And on top, so over here, you have the magnetic field essentially having a direction like this. So you'll have a component upward and a component that way. On the same side, on the opposite end, let's say the bar magnet's centered within the loop. You have a component up and a component that way. So this is the magnetic field. This is the vertical component. This is the horizontal component. And as you go all the way around the current loop, the vertical component is the same. So the vertical component is not going to contribute to the force on the wire, because the force on the wire in the uniform magnetic, the force on the loop of wire in the uniform magnetic field is 0, as you see in the slide. But this component varies in direction all the way around the loop. And in fact, if you set up your DS for this thing all the way around the loop, you can show that the force is going to be the circumference times the current in the loop of wire times B sub x, if this is the x component. Okay? This is a simple example where the force on the wire in a non-uniform field is not 0. And you have one in the worksheet that's due. That one's a fairly straightforward one. Okay, so let me do an example. And I'm going to do the example the easy way and the hard way, because the easy way, I'm just going to use this prescription. It's going to allow you to do several homework problems. And then when I do it the hard way, it's going to allow you to do the worksheet. So I'm basically going to kill two birds with one stone, basically, in this example. Yeah, I'm so, you know, and I couldn't draw. You're right, Patrick. The loop of wires perpendicular to the bar magnet. Oh, I'm sorry. I misunderstood your question. Yeah, the current's perpetually circling. Okay. A lot of times when we draw a loop of wire, really what we mean is this. Okay, Patrick, that's what we mean by a loop of wire. We ignore this thing. There is a battery connected to it, but it's down here somewhere. So it's approximately a perfect loop. Yeah, you can look at one of the loops in the coil, right? You can focus on one of the loops in the coil. Not the end loops, but the ones in the middle. Okay, so I want to do this example. So we have, and you have in the homework, the shape of the wire is parabolic. And you want to do that, the one in the homework, the easy way, not the hard way. So we have a portion of a wire carrying current is 5 amps, it's bent into a semicircle of radius 0.25 meters, and it lies in the first and second quadrant of the XY plane. The current is directed counterclockwise in the XY plane. And you're given the field, and I want to calculate the force on the wire. So let me draw this. Let me switch views again. So let me draw this. Okay, that's better. And the current's going like that. Actually, I'm not, I don't even have this, sorry. And so the radius of the loop is r. And I know f I can also write df and the magnetic field is out of the plane. So I'm going to draw the magnetic field. I was going to get a different color. That means out of the plane. Okay, that's in the z direction. The z direction comes towards us. So I actually want to do the problem this way first, and then I'll do it that way. So I'm going to do it the hard way first. This will help you do the worksheet. Okay? And the reason why I want to try to do it this way is because, well, the current's changing direction relative to the magnetic field. So, actually, I should just say the current's changing direction. It's not changing direction relative to the magnetic field because it's in the plane. It's still in the plane. So I want to write my expression for ds in the direction of the current. So I want a little element of current ds that points in that. This is the direction of ds. This is the size of ds. This is the radius. This is d theta. What's the magnitude of this length? Right, it's an arc length, isn't it? Yeah, what's the magnitude of ds? Well, in terms of r and an angle. Isn't that an arc length? And then the direction of this vector. How do I get the direction of this vector? Let me draw another coordinate system. If this is theta, that's theta. Isn't that 90 minus theta? And then ds is a component to the left and a component upward. So the component to the left is minus cosine of 90 minus theta. Can I rewrite that? I don't want to write cosine of 90 minus theta. What's another way of writing cosine of 90 minus theta? You trig experts, tell me what's another way to write cosine of 90 minus theta? Isn't that the same thing as sine of theta? Right? So I'm going to write sine of theta. And then the vertical component is sine of 90 minus theta, which is, that's my ds. Okay. So B is B naught, some constant, times k hat. So my df, I'll write it up here in the darker color. df is going to be I ds cross B and I want to integrate this thing to get F. I integrate around the semicircle. My B naught is the 1.8 Tesla. Okay, so I got to do I cross K, and so let me draw a coordinate system. Let's do it that way. That's a right-handed coordinate system. What's I cross K? So what's I cross K? Isn't it, I'm sorry, not, yeah, I cross K. I cross K is in that direction. So I cross K is minus J. What's J cross K? Is I hat. So let me rewrite this. After evaluating the cross product, so I have a minus and a minus J. I get that. Now I'm going to integrate. So I want to do this one first. What's the integral of what's the integral of cosine theta? What's the integral of cosine theta? Isn't that minus the sine of theta? What's sine of 0? It's 0. What's sine of pi? It's 0. So then that integral is 0. Now, the other integral, this one's easy. The integral of this is minus cosine theta. Actually, the integral of this was sine of theta. The integral of this is minus cosine theta. And so when you put the limits in, this gives you 2. I think I'm going too low. Hold on a second. Okay. So then I get 2 times the current was 5 amps. R is 0.25 meters. You get 4.5 newtons. We okay with that? So I did it the hard way. I'm going to do it the easy way now. I'm going to use this. So I'm going to use F. And if the field is uniform, the L is the displacement vector from here to here. That's my L. So my L is minus 2r I hat. Is it okay now? Okay. So my L is just minus 2r I hat. So then this is not going to be hard at all. I cross k is minus j, and there's another minus sign. I get the same expression, and I'm done. Obviously, that was much faster, right? But I did it both ways so that I can show you how you set up the integral. So in this particular problem, if b didn't vary, if b varied with position, at least if we part of the integral, you just integrate it. Oh, it's a j. Yes, you're right. Are we okay with that? Okay. So here's an interesting question. We have a bar magnet, and you have a wire carrying current I, and the force on the wire is determined to be upward. And I want to determine what are the north and south poles of the magnet. Yeah, Morgan, you got that pretty quick. So, the question is, how did you get that so quick? And so we have to use the right-hand rule. So let me erase the board. Let me draw, I like drawing my right-handed coordinate system. So we have a current going this way. We have a force upward. And you got to ask yourself, what should the direction of the force be, the magnetic field be, so that the force is upward? Yeah, and it doesn't matter whether you use traditional current or electron current, because what I said before, current depends on the product of Q, hopefully this shows up okay, and the drift velocity. So both of these reverse sign if you use one or the other kind of current. So it doesn't make a difference. If I guess that the magnetic field points to the left, point my fingers in the direction of I, curl them towards B. Oh, I was correct. So the magnetic field points that way. The magnetic field lines go from north to south. So that means that in the case of our bar magnet, this is the North Pole and this is the South Pole because the field lines go from north to south. Does that make sense? So another application of magnetic fields is the following. Your loudspeaker or your speaker. And you can verify for yourself. And remember, I showed you the equation for the force. I'll show you it in a minute. But you have a permanent magnet on the left. I think it looks like a letter E in gray is a permanent magnet. And around the permanent magnet, there's a coil of wire. Those little black dots on the speaker cone represent the coil of wire going around the permanent magnet. So you have a bunch of loops of wire in a non-uniform magnetic field. And the current is not constant, the current alternating current. Okay, the current's not constant. So you have this time-varying current that goes through the loop of wire, and that's going to produce a force in the loop of wire, but the loop of wire is connected to the speaker, is tied to the speaker, and that's going to force the speaker to vibrate in and out. And the vibrating cone causes air molecules to vibrate, and that's what produces the sound that you would hear from it. So that would be an application of this idea of force on a wire in a magnetic field. There's an easy way to create a simple speaker, and unfortunately, I don't have the power supply to do this. But if you take a cup and put a nice little magnet, I have two magnets. These are strong neodymium magnets. I don't know if you can you see the magnet inside there? And you put it inside a coil of wire, and then you run alternating current through here, you'll get this cup to vibrate. You'll actually hear a sound from the vibration of the cup. Okay. Similar idea to the loudspeaker, except that my design is a little bit different. I don't have a permanent magnet around the speaker cone. Okay, so when I get my power supply, probably next week, my power supply that varies with my alternating current power supply, I will use it, and you'll be able to hear a sound being played from this cup. I have one also with a plastic cup. The sound quality will be a little bit different, but you'll hear the sound. I do have your signal generator that came with your kit, but that power supply is so small I can't really do much with it. So I'll bring one from campus, and I'll play around with that during the lecture. So by the way, those numbers that you see come from the equation I showed you before. So for the bar magnet in a non-uniform field, the force was, I don't know if you remember what I wrote down, 2 pi r times the current times the magnetic field. Really, it's the component of the magnetic field that's in the plane of the loop, but the value that you're given in the problem there is the component in the plane of the loop. Okay. So the next topic I want to talk about is what happens if you put a loop of wire in a uniform magnetic field? I don't want to do non-uniform magnetic fields for this because it's a tough calculation. So in the figure I show you, I have a loop of wire in the magnetic field. Let's pretend that magnetic field is uniform, okay? And so the field points from the north to the south pole. So the green line in the figure on the right the green line represents the direction of the magnetic field. This is a top view of the loop of wire. So if you take a look at that loop of wire, and consider the force on that whole loop that's in the magnetic field, and you go around, if you look at the horizontal portions of the loop of wire, the top horizontal portion and the bottom horizontal portion, they will not experience any force because the current is either parallel or anti-parallel to the magnetic field. Because remember, the force is IL cross B. And so if you have two vectors that are parallel to each other, the cross product is 0. So the top one and the bottom one, they're not going to experience a force. It's the vertical ones on the left and on the right. Oops. What happened? It's the vertical ones on the left and on the right. They experience a force. The one on the left carrying current upward in that magnetic field that points to the right produces a force on that wire that's into the plane of the screen. Just use the right-hand rule. On the other side, the vertical wire is carrying current downward in a magnetic field that points from left to right. The force comes out of the plane of the screen. Those two forces, if the field's uniform, are equal and opposite. So on that loop of wire, there is no force. Well, and we established that before. So the total force on that loop of wire is 0. But is that loop of wire in equilibrium? That's my question. Is that loop of wire in equilibrium? The sum of the forces equals 0. No, and why not? Well, kind of, but I think you mean it's similar to the dipole problem. You're right, it is similar to the dipole problem. If there's no force and it's not equilibrium, what's acting on it? In other words, here, let me change views. If I had it's the same example I use it when I teach physics A. Here. If I have a square plate pinned at the center, and I apply a force here, and I apply a force here, the sum of the forces equals 0, but that ain't in equilibrium. Why? What other thing is not 0? Yeah, the plate will rotate because there is a torque on that plate. Similarly, there's a, yeah, there's a moment on it. That's the term we use, the statics course uses. So there's a torque on the plate, and in this loop of wire, there's a torque acting on it. And so what we're going to do is derive an expression for the torque on the loop of wire. And in order for us to do that, let's take a look at the loop of wire from above. So the bottom right hand picture is a view from above. And if you look at it, the black is the loop of wire. At the end shows you the direction of the current in the loop of wire. The black is basically the width of that loop of wire. And we want to calculate the torque. And of course, remember, torque is R cross F. Right, torque is R cross F. And F here because we're assuming the field's uniform. And everything's perpendicular to each other. All right, I is perpendicular to B, etc. So I can write this, the force is ILB. And then if I want to write it as a vector, I can put plus sign or minus sign depending on whether it's the force is in or out of the plane of the page. Okay. I can do the same thing for the torque. Anyway, but we can calculate the magnitude of the torque. The magnitude of the torque is going to be the magnitude of R times the magnitude of F times the sine of the angle between F and R. So let me draw this represents the current coming towards us, the current going into us. I'm sorry, into the plane. Okay. And the magnetic field is this way. So F here points downward. F here points upward. This is phi. This is phi. And then if this is the normal to the loop, that's phi. So the torque is going to be let's calculate the torque about the center of mass of this thing. If this distance is W, this is W over 2. So the torque is going to be the vector R cross F. R is going to be W over 2. F is going to be I times L times B. And then the angle is the angle between the R vector and F. But similarly, this does the same thing. Since the vector R is pointed in the opposite direction of this one, and so is the current, they're going to produce the torque in the same direction. What's length times width? It's area. Now phi is the angle between the normal to the loop and the magnetic field. Okay? W is the width. right? The length goes into the board, right? Because remember, we're looking at the top view of this thing. So we're looking at the top view. Let me draw somewhere else. We're looking from this way. Are we okay with that? Because torque is a vector. The torque vector is going to be perpendicular to the force and the r vector. In fact, the torque vector is going to be pointing straight up. So really, I can write this as a vector. I can write the torque as a vector. But I have to define something to do that. Oops. And I wrote the area as a vector. And really this is the area times the unit vector that's normal to the surface. This is called the magnetic moment. The magnetic dipole moment. It can also be written this way. Instead of using the letter mu, you can use the letter B. But A is just the area vector, the magnitude of the area times the normal to the surface. So that's how you write the torque in terms of vectors. You have to define this thing called the magnetic dipole moment. Okay. So if you imagine an electron going around in a circular orbit, the electron has its own dipole moment. It produces a magnetic field. And one can write the magnetic dipole moment of the electron in terms of its angular momentum. And that's discussed in your book, and you should read that in your book. Okay? Now, one thing I've neglected is that my equation assumes that my loop of wire has one turn. But in reality, you can have a loop of wire with many turns, like this one. This has more than one turn. This has more than one loop, right? So if I have many loops, or n loops, then I should multiply this by n. So this is for one loop. So if I have n loops, then I got to put an n here. So mu okay? So here's a question. We define this thing called the magnetic moment for a loop of wire carrying current. So here's a loop of wire carrying current. Let me just do it. It can be a square loop or a circular loop. Let's say we have something carrying current like this. How do you define the normal to that? Because the normal, there could be one normal pointing towards us and one normal pointing into the plane of the board. Which one do I use to define this? I use another right-hand rule. Everything here, the cross products are defined by the right-hand rule, right? So I use another right-hand rule to define my normal. My normal to the surface is defined by the direction of the current. If I curl my fingers in the direction of the current, my thumb points in the direction of this vector. I curl my fingers in the direction of the current, and my thumb points in the direction of mu. That's the normal I use. That's the normal to the surface that's what defines the direction of the normal to the surface, because otherwise it's ambiguous. I'm not sure. I have to have different currents? Oh, yeah, sorry. I don't know what I was thinking. I don't know why I do those things. Sorry about that. That better? Okay, sorry about that. I guess I should have drawn a circle. I probably wouldn't have screwed it up. Okay? So thanks for pointing that out. But again, you just curl your fingers in the direction of the current, and then your thumb points in the direction of the normal to the loop, the one you want to define. So where would this be useful, this idea? And I only have a couple of minutes. Where would this idea be of any use for us, or in the real world? Why would you want to get a magnetic field to rotate a loop of wire? Yeah, and motors, the electric motor. So in lab, I'm going to talk about the electric motor. Okay. Now, so I'll use the lab to talk about the electric motor. Just want to say a couple of things. So most of the problems where you're going to calculate torque, the problems are pretty straightforward. A lot of them are just plug and chug, because if you want to use this equation for a non-uniform field, it's not a fun calculation. Okay, so we don't do non-uniform fields in this class. Okay. But I do want to mention one more thing, is just like the electric dipole stores energy, if you remember, the electric dipole store energy, and it was given by the magnetic dipole stores energy too. How do you get that? Well, you have to integrate the torque. And of course, the torque depends on the sign of the angle. When you integrate, you get the sign, and then you can write this as I'm doing it quick. When you integrate this between the limits, then you'll get a minus the cosine when you do this integration. Okay, and that's where this comes from. You write it as a dot product. It's the same process as we did for the dipole. And so, in reality, one can spend a lot of time just discussing this and this. Unfortunately, I don't have a lot of time in the course to talk about it. This has a lot of significance when you talk about the atom or the electron in the atom. But due to time constraints, it's hard for me to do it. If this was a junior level course, I would probably spend a significant amount of time describing this and its implications. I mean, I know I did something like this for the electric dipole. I just don't have enough time to talk about the magnetic dipole. Okay. There's some important things one needs to talk about, but we can't do it here. All right. Okay. So when we meet in the lab, I'm going to take your questions on the experiment. So I hope you have questions on the experiment. Some folks, for some reason, don't have the 560 ohm resistor. And if you don't, I need to know, because when we can contact Tyler and Tyler can get it to you. And I actually had one student just go to Fry's and get the resistor, because it's like, they're real cheap. Okay, they're like $1 or $2. But usually you can't buy one resistor. They usually give you a bunch of them. Okay, so anyway, I'll see you folks in less than 20 minutes. So I'll talk about the lab and then I'll finish the chapter. Okay, I'll see you then.